Hello, this is team number 6 with our GRP. We'll be presenting nanographene today. To begin, we have our outline and we'll be going over the 5 main points. The state of the art, the synopsis of problems being solved, solutions to those problems, limitations and the proposal implementation, and the conclusion. Let's get started. Hello, this is Julio Hernandez with our nanographene presentation. I'll be going over the first part, the state of the art of nanographene. So to begin, graphene itself is a modern material that is seeing a lot of use, development, and advancements in the nanobiological and medical fields, as they offer electronic, thermal, and mechanical properties that see much diverse use in those fields. And well, we'll go on. They are constructed by placing copper foil in a furnace or argon gas. The carbon atoms are then added into the matrix. It is then spun approximately 3,000 times per minute. It is then finally split apart and placed in a silicon chip covered in gold pellets and plasma. To the right of we can see an image that allows you to visualize the construction process. But I highly recommend looking into this yourself if you're ever curious. And graphene itself, once this process is done, will create a material that is very flexible, conductive, and it comes to be an atom thick, and it is approximately 200 times stronger than steel. And for the sake of nanotechnologies, synthesizing graphene, this graphene, can produce nanographene oxide, or NGO. This allows for the sheets to be a few nanometers in lateral width, and they are then pegylated for biological applications. And on that note, currently in the state of the art of graphene, of nanographene, graphene is used mostly for cellular imaging. NGO sheets are known to be greatly photoilluminescent, which allows for live cell imaging, and accurate one at that. I again recommend looking into this yourself if you're ever curious. Additionally, the cancer drug, I'm sorry if I mispronounced this, doxorubicin, can be loaded and distributed with ease using NGO sheets, with the addition of physosorption via pi stacking. What this allows for and this works as an antibody that can selectively destroy cancer cells seen mostly under in vitro conditions. Graphene has also been known to aid in the detection of glucose, cholesterol, and hemoglobin level such amounts. So, as due to their nano size, their properties, low cost, and usefulness, NGO has been proving itself to be a promising material in the nanobiological and medical advancement. So, again, highly recommend if you're ever curious to keep looking into this, but I'll be passing it off to my partner now.
Part 2 Synopsis of Problems Being Solved. First listed issue with graphene is its ability to be mass produced. It has a fine and delicate process as shown below in the photo here. When producing graphene, errors such as wrinkles in its single layer or unwilling doping must be avoided in order for graphene to work as it's intended to be. Unfortunately, in a mass-producing environment where a machine must exfoliate graphene mechanically with force, it has a huge potential of ripping it. Such errors will occur and always occur, thus making its manufacturing process harder. As my partner previously mentioned, one common method of producing graphene is by a process called chemical vapor deposition, or CVD. The two problems with this is that it takes a long time to make with little graphene produced, and the quality is not adequate. On to the second issue. The second listed issue with graphene is its ability in being a good conductor, better than copper. The reason for this is that graphene does not have a band gap, meaning it cannot be turned off. A constant flow of electrons will continue to pass through the material. Band gap is important because it determines the color and conductivity of a semiconductor. With graphene's higher energy band gap, it has the ability to produce higher temperatures, which means the flow of free electrons increases. If we take a look into the table provided below, we see that graphene has a higher conductivity than copper, meaning that it is easier for electrons to flow via graphene than copper. These are the two issues listed within our project in which a solution was mentioned for.
Hello, my name is Joel Gonzalez, and I will be presenting on section 3 of our presentation, Solution to the Problem. Now at the time, the graphene is not unlike many other special materials in where it suffers from production issues. And for this presentation, we will focus on nanographene oxide. And now at the time of this presentation, there exist two methods of production: chemical vapor deposition, which we'll call CVD, and exfoliation from graphene. Now, CVD will create higher quality graphene due to it mostly being single layered, but we should also note that this method of production is more expensive and has a very slow production time. Now, in contrast with exfoliation from graphene, we can see that it involves more chemicals and mechanical stresses, which overall lead to a lower quality graphene, but with the trade-off that it is cheaper and it is much quicker to produce. So, to conclude, there are still issues with production of graphene, but there are temporary workarounds for specific needs and or purposes. And now, while there is still work to be done, graphene is improving as a conductor.
Alright, this is the limitations in the proposal implementation for graphene. Problems with graphene. Although graphene seems to be a very appealing innovation, it does have some limitations which have caused delay for its widespread use for the promising material it's said to be. One of the problems with carbon nanotubes is that they come in different patterns, shapes, and sizes, and the risk depends critically on what type of carbon nanotube we are looking at. Another implementation aspect is the chemistry of graphene matters. These often come with additional chemical passengers like metal nanoparticles used in this production or chemicals added to the surface to make them easier to work with. So here, what we see is we do see some patterns here of graphene. And this can be a problem because when it comes to the biomedical, if these are going into humans, we do need to know which one to properly use, which pattern to use, as their differences can cause different reactions in this case. So that is a problem in manufacturing them, to make sure that we separate and not contaminate while doing this separation of the graphene, so we can just make sure we have it remains pure, as purest as it can be. And this is more problems with graphene. Like mentioned before, sometimes they add additional chemicals, metal nanoparticles, of course, where they're trying to separate them. And sometimes they do add chemicals under surfaces, of course, so it could be easier to work with, so they can separate them easier and stuff like that. And yeah, sometimes they also add, in this case, another example is the drug molecules. They go ahead and add them also so they can be more effective when it comes to treatment. Here in this picture, we could see a impurity, a defective sheet of graphene. As mentioned before, these are hard to make. Sometimes they do come out with impurities, and of course it does cause problems. And this is a image where you could clearly see here. And so pretty much the problem is just that it's right now, and the world we are right now, it's hard to manufacture them since we're talking about the nanoscale, and it's also hard to, of course, make the right patterns, separate them, manufacture them, and also the uses of them in human bodies and machines, computers, all these things. It's super hard to manufacture. It's also costly, and right now with the current competition, it is expensive, and Right now, silicon is a more optimal material as it's cheaper, more reliable, it's abundant, and it's not that hard to make. And it's also a good semiconducting material as well.
As we saw in this presentation, we know that graphene is a superb material with its limitations. We know that graphene is 200 times stronger than steel, is extremely flexible, it is a superb conductor, and acts as the perfect barrier. Not even helium can pass through it. It's the thinnest material possible, with it being 1 atom thick and being transparent, and it absorbs 2.3% of light, and it can be seen with the naked eye. Within this project, we discussed about its manufacturing process, such as it going through CVD, chemical vapor deposition, and also exfoliation. We also talked about two issues found within graphene. One of the issues is it being in its ability to be mass produced. Graphene is very delicate and fine that mass producing it would always have its errors, and unfortunately with graphene there can be no errors in manufacturing it. Another issue that was found within graphene is its ability to be a good conductor. This may seem odd, as that scientists are always striving to find a good conductor that's better than copper. We know that copper is very expensive and very malleable. The thing with graphene is that it has no band gap, meaning that a constant flow of electrons will continue pass through the material, meaning it can't turn off. This is an issue because it can harm not only our electronics, but it can also harm any human applications that would want to be used with graphene. We discussed about solutions within these issues. One solution to the manufacturing process is its constant advancement and better process in CVD, and chemical vapor deposition. We can continue improving its process and finding better ways as we go along the years. Newer technology, faster processors, everything. So as we continue with the CVD process, it will create finer and quality graphene. Overall, it may be said that graphene is a fairly new innovation that is currently being researched by a large number of people all over the world. With current manufacturing issues such as converting small flakes of graphene with variable thickness to large sheets, it will take time for graphene to become mass produced. New applications are currently being developed and can be groundbreaking if and when they are utilized. These applications of graphene can further technology and open doors for other groundbreaking discoveries.